Hi, so this video is going to discuss item number 1 in your last module. It's the module that I was discussing prior to the suspension of classes, the one discussing power factor improvement. I believe I forwarded the file in our GC for 50 years because back then the portal wasn't working well. So, yeah, I'm just planning to give a couple of modules for the online learning and one activity for each module. Don't worry because these are going to be very easy activities. They will probably just contain some couple of items you can work around with while you're at home there. So, yeah, before we start solving the first example, just a recap. We what we basically just need to recall when dealing with such problems on power factor correction are two things. Number one is that power in AC system has types or three forms rather. So it can be the power dissipated by your resistive elements, which is the real power. And remember, it can only go one direction. It can't go the other way because we don't have such thing as um negative real power. And yeah, the next one is your reactive power. And this is now going to depend upon the nature of the load. Um, if the load is inductive, then you are going to have a reactive power opposite that when the load is capacitive. And it's a quadrature component of your real power, which means to say it must be drawn perpendicular. So it can go upwards or downwards. Say upwards is for an inductive load there. And of course, we have the vector sum of the two, which is now your apparent power. The angle between the vector of the apparent power and the real power is your power angle. There. This is where your power factor comes in because your power factor is, I'm sorry, your power factor is the cosine of the power angle. And we've talked about this during our lecture that there is always a need for us to improve the power factor. The highest value of power factor you can call is 1, and that can only be attained if, since this is a cosine function, a value of 1 can only be attained if the angle here is 0, right? So which means you need to be closing this power triangle. This must be closed. So the S must approach the P in order for you to have a unity power factor. And the reason behind is mainly economical. So you can just go check your notes for that. But the process, of course, is going to entail the use or the insertion of capacitor banks in your capacitor banks if you have a polyphase system, right? So if we are going to consider this triangle to be the power for an inductive load, then Q being directed upwards is going to have an opposite direction that for a Q caused by a capacitive element. So that Q this time is going to be downwards. So it's going to be reducing this Q. This one, which is directed downwards, coming from this point going down, that is the reactive power offered by your capacitance. Of course, if it's the other way around, if your load is already capacitive in nature, and then you're going to be adding capacitor, then the Q capacitor is going to add to the original value of Q. Whereas for this one, we're just considering that this is a diagram for a load which is inductive. So this is actually going to be the decrease in the value of your reactive power when you have installed already your capacitor banks. So if there's going to be a decrease, so you will now have a new or a final value of Q being the original value of Q minus the Q offered by your capacitor. And from there, you can see that this triangle is now going to close out because the angle is going to decrease. And if the angle decreases, your power factor now increases. That's the first thing you have to remember. Now, regarding the values, the original to the new values, that's going to depend upon the type of correction that you are implementing or the type of problem that you are solving. What I'm trying to say is, will there be a change in power? Will there be a change in apparent power? There will obviously be a change in reactive power because you will be installing capacitors. So, regarding with regards to change in real power or change in apparent power, that remains to be seen depending upon the type of problem that you are trying to solve there. And secondly is, of course, again, as we've said, the improvement of power factor can be done by installing capacitors. So the other thing that you have to recall is, how do you solve for this Q offered by the capacitor? It's not a very difficult formula to recall if if you're dealing with a single phase system. So you simply tap the capacitor across the lines. You only have two lines for single phase, right? So if this is the voltage of the line, then how do you solve for Q here for a single phase system? This capacitance written in C, you can determine its capacitive reactance using the frequency of the system, usually 60. You can obtain your XC so that the Q of the capacitor here, the Q offered by the capacitor is V squared over XC. It's a very familiar formula because you also have V squared over R when solving for real power. You also have I squared R for real power, which means to say you can have I squared XC also for Q capacitor. However, I is not usually given. It's the voltage across the terminals which is usually given. So very simple for single phase. For three phase, you can again you can install capacitor banks in delta or in Y. So it depends how you're going to be installing them. So if you install them in, say, delta, say you have three lines here. So you may install a capacitor from one line to another capacitor from one line to another, then from one line to the next here. And you have here your voltage. Remember that The only complicated thing about three-phase systems is that you have two voltages. You can have two voltages, especially if it's three-phase four wire, because the fourth one is your neutral. So if you're taking the voltage across these two lines, that's your line to line voltage. So which means to say the Q capacitor here will be VLL squared over XC. XC again being the capacitive reactance of each of these capacitors. However, that's not the only way you could connect your capacitors. You could also connect them in Y. So if you connect them in Y, if these are your three lines, say this is line A, line B, and line C, you should have here a fourth line, which is your neutral. And you can have one capacitance connected from A to neutral, another one from B to neutral, and then another one from C to neutral. So this time, the capacitors are connected in Y. So if this is the case, then the Q offered by these capacitors will be equal to V line to neutral squared over XC. Wait, I forgot something. This must be multiplied to 3 because you have 3 capacitors. Similarly for this one, if you do not want to solve for VLN, VLN is VLL over square root of 3. By the way, this must be multiplied to 3 there. And you have to square this and times 3 divided by XC. So this will become VLL squared. Square root of 3 squared is 3. 3 cancels with this one. So for a Y connection, your Q capacitor, let me continue it here, must be equal to VLL squared over XC. There. Which gives us now the conclusion that the reactive power offered by the capacitor bank connected in delta, this one is in delta, is 3 times higher than that when it's connected in Y. There. Okay? So those are the only things you need to recall. So answering now your number 1. So your number 1 states an alternator is supplying a load of 300 kilowatts at a power factor of 0.6 lagging. If the power factor is raised to unity, how many more kilowatts can alternator supply for the same kVA loading? So we have a very important statement or a very important phrase at the last, which is the for the same kVA loading phrase. So if we're going to write the given, 300 kilowatts is our original power. Power factor is originally 0.6 lagging. And we are now going to raise the power factor to unity. So this is power factor 1, power factor 2 is now 1. Let's just solve for the angle, original angle of the 0.6 power factor. So just take the inverse cosine, of course, of 0.6. Hope you still can recall these things. Which is equal to 53.13. Whereas for the unity power factor, the original angle is, or the new angle rather, is the inverse cosine of 1, which is apparently 0. The question is, how much more power can we accommodate if or for the same kVA loading? So that's very important because we know that S1 is the same as S2. There. So I'm going to draw the original triangle. So this is the original triangle. Oops. Let me repeat that. There. This one is the real power. So it's 300. And the original angle here is 53.13. Now, since the new angle is going to be 0, imagine that this angle is now supposed to become a new triangle. And you do that by not changing the hypotenuse. Why is that so? Because when you don't change the hypotenuse, the length of the hypotenuse, it's now trying to implement this equation. S1 must be equal to S2. By the way, this is S2. I wrote this one very poorly. There. So how does the triangle look like when the angle is 0? It doesn't look like a triangle anymore. It's just a straight line, right? So which means to say this one must close. This one must close there, right? So it must close so that the power angle will become 0. And if it closes, what happens is at that condition, your S2 is now similar to your P2. So there's no such thing as S or P. There's no difference anymore between the S and the P. It's just a single value. If it's 500 kilowatts, it's also 500 kVA. So how do you solve now for the additional power that you can accommodate? Because it's very clear from this diagram that the real power is going to increase once this triangle closes. So of course, we can solve first for the original value of your S. So what is S1 in the first place? So S1 is equal to what? So we have an angle here. We have an adjacent side and we have your hypotenuse. So what function do we need? We need the cosine function. So cosine of 53.13 is equal to 300 over S1. 300 over S1. So S1 is 300 over cosine 53.13. Oops, sorry. 53.13 there. So 300 divided by cosine 53.13 gives us 499.9988 kVA. There. Now remember that this, at the same kVA loading, this is now also equal to your S2. And remember that at unity power factor, S2 is also now the same as your P2. Which therefore means I'm running out of space. I'm going to make a space here. Yeah. There. So which now means we have a P2 of 499.9988 kilowatts. Please wait, I'm messing up my brush size. There. So which means our P2 is 499.9988 kVA. So again, we go back to what the problem was asking. How many more kilowatts can alternator supply for the same kVA loading? And the answer is, of course, how much was added. Oops, no, I don't like to use that. So how much was the change in power? So obviously this is P2 minus P1 there. So answer must be 299,199.9988. There. Okay?